Alright, I'm recording the last video for 114. So this is lecture 20, okay? So the last thing we want to discuss is going to be E&M waves. Of course, E&M waves is a very rich topic. This is only the last lecture, so we don't have much time to really go into detail. We're just going to learn some very basic facts of E&M waves, okay? First of all, let's take a look at slide 1. So in 1860s, Maxwell, so in 19th century, there are a lot of research on E&M, okay? People discovered many laws, okay? But Maxwell realized that he can put all these equations, okay, in a complete theory, okay? So, and he only needs 4 equations. So these 4 equations on this slide, you can take a look at them, and then we have already learned most of them, right? Like the first one, Faraday's law, okay? No, I'm sorry. The first one, Gauss's law. Then the flux, electric flux, right? Through a closed surface, always equals to the charge inside divided by the epsilon naught, it's constant. And then he just wrote the charge as the integral of the charge density. The rho is the density over volume, right? And Gauss's law for magnetism, we didn't really study that, and then but it's very similar to Gauss's law for electric field. The only difference is that the right hand side is 0 because there's no magnetic monopoles, right? So it's very similar. You see the symmetry between the electric field and magnetic field. Faraday's law, that's the third equation he listed. And then we learned that Faraday's law, it's the induced EMF equals the change in flux, right? And then he rewrote this induced EMF, which is just the voltage, as the integral of the electric field along a path between any 2 points. That's the definition of a voltage, a potential difference, okay? And then the fourth law, we didn't really discuss that, but that's called Ampere's law. That's also equation for the magnetic field, the integral of the magnetic field along a path. You can see the symmetry, okay, between all these equations, right? The first 2 equations, they're totally symmetric. The last 2 equations, totally symmetric. So Maxwell didn't really discover these 4 equations himself, but he's the first person who realized E&M, they're definitely connected. And then the theory, the whole theory for E&M can be summarized in these 4 equations, nothing else. So that's why now we call this set of equations Maxwell equations. And they're very beautiful, okay? A lot of physicists list the Maxwell equations as the most beautiful equations in physics. Because look at the symmetry, right? Yeah, whoever created this equation, that must be God, right? He created this universe with such a beautiful theory. And E&M, they are just they are not separate field, they're just 2 components of the same field. And then I don't think you're going to study advanced E&M theory. When I studied advanced E&M theories, we don't have a field called electric field or magnetic field. We have a tensor which has 8 components, and then this tensor is the complete quantity to describe a field called an E&M field. So there's no electric field or magnetic field in nature actually. There's only one field called an E&M field. It's just the physicists discovered the electric field and magnetic field separately. We thought that E&M, they are, totally independent, separate, but no. Actually, they're just 2 components of the same field. Think about space-time. I can give you another example. Before Einstein, people thought that space and time, they're totally independent, right? They're not going to be connected. We live in a 3-dimensional space, and time is another dimension. It has nothing to do with the space. It just always flows at the same rate in one direction, always forward. And Einstein realized this is not true. This is not true. We live in a four-dimensional space. Time is just another, a very special dimension in this universe. Now we call it space-time, right? So we live in a four-dimensional space-time. So time and space, they're just four dimensions, four different dimensions of this universe, but they're definitely connected, okay? So that was actually a very big discovery in physics, because what he did, he didn't just realize that, he also combined these four equations. He wanted to solve these four equations, okay? And these four equations on slide 1, they look very scary, okay? I'm not going to ask you to remember these. I'm not going to ask you to solve them. I just want to tell you their consequences. So Maxwell, he wanted to solve this equation. He started with the simplest case. The simplest case is that, okay, if I solve these four equations in a region where there's no charge, no current, okay, what do I get? In that case, you just get the rho e, the charge density, is 0. Then this Je, which is the electric current density, also 0. You get these two zeros, you put them in, you solve these four equations. Okay, you can definitely solve them. They are differential equations, but they can be solved. They can definitely be solved. So once he solved these four equations, he get the solution for the electric field and magnetic field. Right? He combined these four equations, and then he wrote. He found that the one complete equation for the electric field and the complete equation for the magnetic field, again, look at these two equations on slide 2. The first two equations, totally symmetric, totally symmetric. And then if you are a physicist, when you see these two equations, you know what the equations they are. They are wave equations. Even at that time, in the 19th century, okay, physicists already knew wave theory. So Maxwell solved these two equations, then he got these two solutions, and then these two equations, these two differential equations, they have different solutions. They're the wave solution. So the solution to this, that's just one equation. The solution to this standard wave equation is listed at the bottom. So both the electric field and the magnetic field, they're going to be waves. Okay, if you solve these four equations, so if you have this E&M field in one region with no charge and no current, both the electric field and magnetic field, they behave like waves. And you can also find the speed of the wave using this fundamental wave theory. Again, all physicists, even at that time, knew about this wave theory. So using this two equations for the electric field and magnetic field derived from Maxwell equations, you can also see that any physicist will realize that, first of all, these are the two solutions. Electric field and magnetic field, they are wave-like. Secondly, these waves, they will travel with the velocity with this number. Where does this number come from? Again, it's a fundamental wave theory, okay? Whatever in front of this partial square, E over partial T square, and then that number, square root, take an inverse, that's gonna be the velocity of wave. That's a fundamental wave theory, okay? So that's just a conclusion from a wave theory if I have two waves like that, okay? Then, okay, so that's the first conclusion, discovery he made. So he predicted the existence of E&M waves, okay? And then we can also understand that intuitively based on the theories we have learned, because we learned that changing electric field is going to produce magnetic field. And we also learned changing magnetic field produces electric field. Then, if there's a change in electric field, it's going to produce some change in magnetic field. The magnetic field is also changing, and then it's going to produce another change in electric field. And then, this pattern just continues, then until you get a lot of electric field and magnetic field, okay, traveling in all directions. Then that's E&M waves, okay? So that's just changing electric field, produces change in magnetic field, produces another change in electric field, produces another change in magnetic field, okay? So it was a really amazing discovery back in the 19th century, because no one really knew about E&M waves, okay? At that time, no one even knew that electric field and magnetic field, they can travel as waves. So that was a very important discovery. And then another interesting thing is this, okay? From these two equations listed on slide 2, you can realize from fundamental wave theory, the speed of that wave, whatever this wave is called, it's going to be determined by these two constants because of that fundamental wave theory. Now what I want you to do is find these two constants, okay, put them in, and then find this value for me, okay? Pause the video, find these two constants from the lectures, and then put them in. This is the mu naught we have been using in magnetic field. This is the epsilon naught we have been using in electric field. All right, so if you have plugged numbers in, okay, you do the math very carefully. What is the number you got? You actually get a very interesting number. And this is also the number Maxwell got when he tried to solve these equations. What is this number? If anyone recognize that, this is the speed of light. Speed of light is this value. And then at that time, physicists also knew the speed. They had already measured the speed of light. They already knew that the speed of light is that value. Light always travels at that value, okay? So this was really a puzzle for Maxwell. Because no one knew that, first of all, no one knew that E&M waves exist. And then secondly, no one even expected that these waves, which never existed back in the 19th century, these waves, they will travel at the speed of light, okay? So this is really weird to Maxwell. But anyway, he still published his results, he published his predictions. He predicted from these four equations there is a solution for E&M waves, and these waves, they will always travel at the speed of light. He didn't know why. He couldn't explain that, but he just predicted the existence of this wave, okay? And then, so that's what he did in 1960s. So in 1886, the German physicist Hertz, okay, he performed the experiment, and then in that experiment, and then that was the first time we produced E&M waves was generated in human history, okay? So what he did was this. So I attached an image on this slide, okay? So what he did, he generated a E&M wave between these two plates, okay? See that he uses some plates to generate get a very strong electric field in that region, and then he used some changing electric field, and then that changing electric field, as I said, is going to create a changing magnetic field, and then another changing electric field. So basically, he just created some E&M waves, and these E&M waves were received by another receiver loop he placed away from this transmitter, okay? And then I also attached a link to a YouTube video, okay, which is going to show you what he did in that experiment. That was the first time E&M wave produced in human history, okay, by human, okay? Because there are E&M waves in nature, okay, all the time. It's just we didn't realize these, like sunlight is also E&M waves. Then why do E&M waves travel at the speed of light? Right now we know the solution is because visible light, it's also E&M waves. So E&M waves have a very wide spectrum. Visible light is a very, very small portion in that spectrum, as we're going to see later. Okay? So that was a huge discovery. And after that, Now you can see that our life, there are all kinds of applications of E&M waves. You can't live without E&M waves, radio waves, microwaves, right? Your cell phone, everything use E&M waves, okay? So again, as I said, we're just going to learn, this was the prediction and the confirmation of E&M wave, the existence of E&M, the history of E&M waves. Now we're just going to learn some very basic facts about E&M wave. First of all, that's slide 6. First of all, E&M waves, they can travel in vacuum, and this is very different than mechanical waves, like sound waves. You can hear me because your ears receive the sound waves generated from my throat and through the air. If I speak in vacuum, you're not going to hear me because there's no medium to transmit the sound waves. E&M waves, they can travel in vacuum. So even there's no medium, you can still receive E&M waves. There's some strong evidence in our life that E&M waves can travel in vacuum. What is that evidence? Pause the video, think about it. There's some strong evidence that E&M waves, they can travel in vacuum and reach us. That's sunlight. Sunlight is E&M waves. Is there anything between the sun and the earth? No, not even air, okay? But they can still reach the earth, and that's actually the source of all the energy on the earth. So that's actually a very important property. Without that property, earth is not going to receive energy from the sun, then there will be no life on the earth. We're not going to be around, okay? And then another property is this: the magnetic field and electric field, they're always perpendicular to each other, and they're also going to be perpendicular to the direction of the wave. It's very interesting. So look at the image on slide 6. So if the electric field is oscillating this way, so you will see the waves going this way, wave-like, right? And then the magnetic field is going to oscillate in this way. Look at the image, okay? And then the wave is going to travel in this direction. So electric field oscillating this way, magnetic field oscillating this way, but they both travel in that way. So all these three directions, they're perpendicular to each other. They form X, Y, and Z, okay? Because we have 3 dimensions of space. So everything is consistent. You think about it. All these theories, they're just like so amazing. Everything is consistent. Everything is complete, okay, in this universe, okay. And then the E&M waves, so you see that the electric field is going to be a sine function, like the AC circuit we discussed. The magnetic field is also going to be a sine or cosine function. So they will have a maximum value, right? Actually, the maximum value of electric field and magnetic field, they're connected by the speed of light. So this is a conclusion. This is a conclusion, again, from Maxwell's equations. Everything's going to be a conclusion from Maxwell's equations, okay? So they're connected by this C. Okay, how do we derive that? I'm not going to show you it. Okay, this is not what we're interested in. This is just one fundamental fact we want to know about E&M waves. And then that's something we usually define for E&M waves, okay? A parameter we define for E&M waves. When we study E&M waves, that's called intensity. Okay, what is intensity? Intensity is defined as this. We use the symbol I for intensity, not current. In this case, it's not current, it's the intensity. The intensity is defined as the power of the E&M wave divided by the area. Okay, it's emitting to some area. Okay? And then this is definition of intensity in physics, okay? Intensity of any E&M waves is always defined as power divided by air. You can define anything you like, right? And this is also used in like sound waves or other things. But for E&M waves, this intensity has a very special equation, and this is only true for E&M waves. It's going to be equal to E max times B max divided by 2 mu naught. Mu naught is the constant we have been using, right? And of course, the unit for this guy is going to be watts per square meter. So this is pretty much like power has a general definition, energy divided by time, right? This is true for any energy consuming process, but there's a special equation for circuits, right? If there's a resistor in a circuit, this can be derived. Okay, you can just do current times voltage. It's going to give you this power. This is the general definition of intensity physics, and then in E&M, for E&M waves, so you can derive a very special equation for that. Okay, so that equation can help us make some predictions. We're going to take a look at the question on slide 8, and we're going to see why this is useful. Okay, a radio station on the Earth's surface emits an E&M waves with average total power of 50 kilowatts. Okay, so it's emitting E&M waves, okay, with a certain power, okay. Assuming the transmitter, so take an image, so it's on the surface of the ground, on the surface of Earth, radius equaling all directions above the ground, so it's radiating in all directions. Find the magnitude of the electric field detected by satellite 100 kilometers away from an antenna, okay. So we want to find the electric field detected by the satellite, okay? So we want to see how strong the signal is at that point. So this intensity can help us make that prediction. So how do I use that to make that prediction? Electric field is here, right? So that means if I rearrange this equation, this is the definition of the intensity, but this is going to be equal to this equation in E&M waves. So if I can rearrange this equation, then I can find the electric field, right? The satellite received. Now, do I have all the numbers I need? Mu naught constant, right? Power. Oh, it's telling me that it's emitting EM waves with this power. Okay, so that's the power I'm going to use. Convert it to SI units. Now, the A, what is the A? A is the area of the surface, okay? So this surface, because it's emitting EM in all directions, so the surface is going to be a sphere, but it's emitting above the ground, so the surface that receives the EM waves is going to be at the same distance from the transmitter. It's going to be half a sphere, okay? And then what is the area for half a sphere? Okay, if you remember that, for a sphere, no, can't spell. It's going to be 4 pi r squared. Remember, it's a sphere. Like that, not a circle. Circle is pi r squared. Sphere, the area is 4 pi r squared. What about half of it? 2 pi r squared. Okay? So that's the area I'm going to plug in. What is the radius I use? Well, I want to find the electric field detected by the satellite 100 kilometers from the antenna. So that's the radius, right? That's the region, okay? That's the surface that can receive these EM waves, okay? So the R, it's going to be 100 kilometers converted to SI units. Now you would say, well, okay, I have these two numbers, I can rearrange this equation, but what about Bmax? I don't have Bmax. Bmax and the Emax, they're connected, right? So I can replace Bmax with Emax. So I can do this, equals Emax times Emax over C divided by 2 mu naught. Then now you see that I know everything in this equation. I can rearrange this equation, find Emax. That's going to be the Emax the satellite receives. Okay, pause the video, do the math, and see if you can get the right answer. All right, so let's see. First of all, let's rearrange this equation. If I rearrange this equation, I can, the easiest way, cross multiply. You will get E max squared divided by C times, so you're going to do this, times A equals P times 2 mu naught, right? And then E max, it's going to be P about 2 mu naught times c divided by a square root. Okay, now I'm ready to plug numbers in. I know all these numbers here. If you plug all the numbers in carefully, you should get newtons per coulomb. Alright, so that's the electric field detected by the satellite if it's 100 kilometers from the antenna. Alright, so that's this. Now another thing we want to learn about the EM waves is this wavelength and frequency. Slide 9. I think some people already know these two things. What is wavelength? Okay, for any wave, right? For example, look at the wave on slide 9. The distance between two adjacent crests and two adjacent troughs is going to be a constant, right? If it's a perfect wave, like a sine and cosine wave. If that's a constant, why don't we define it as a property of the wave? So we call it wavelength, right? So we call it wavelength. And then for any wave, so you can use wavelengths to find the velocity. Why? Because for any wave, it's always going to travel one wavelength in one period. So it's like a uniform motion, right? Uniform motion, it always travels 2 pi r in one period, 2 pi r in one period. So you can always do v equals 2 pi r divided by period. For a wave, when it's traveling, okay, it always travels one wavelength in one period. So that means I can connect these three guys. The speed of a wave, it's going to be the distance over time, right? So I would do, in one period, it's always going to travel one wavelength. So distance over time. And then, if you remember that, we define frequency. For any periodic motion, we always define frequency as 1 over period. So you can use that to describe how fast this thing is oscillating, okay? So in that case, you can get another form of this equation, and this is actually more widely used than this equation, wavelength times frequency, okay? So the speed is going to be wavelength times frequency. So this is not like a special equation for speed, right? This is still the definition of speed, but in waves, it's always going to travel one wavelength in one period, okay? So, and then you make use of the relation between the frequency and period, so you can get V equals the wavelength times frequency. So, as I said, Maxwell predicted that all EM waves travel at the speed of light. So the speed of any EM wave in vacuum is going to be this time, but there's no limit. There's no limit on this on the frequency and wavelength, right? So that's why EM waves have a very wide spectrum. Take a look at the image on slide 10, right? So, because then there's no limit on these two guys. As long as the product is the speed of light, that's going to be a EM wave. So EM wave can travel at different wavelength, different frequency, as long as the product is this value. So you can see that, and then we do have some names for the waves, EM waves in different ranges, okay? For example, on this low frequency end, we call them radio waves, and radio waves are widely used every day, right? Microwaves, after that, we use microwave to heat up food. Infrared wave, and then visible light, it's going to be it's a very small portion, right? And on the other end, you get ultraviolet, X-rays, and gamma rays, okay? And I also attached a link to a YouTube video which explains this spectrum and the application of these different waves in real life. It's a very interesting video. Check that video, okay? Now let's take a look at the question on 11. Let's just practice this special theory for wave speed. An electromagnetic wave travels in free space, okay? The distance from the crest and the adjacent trough is 3.5 meters. What is the frequency of the wave? Okay, if you see them waves, you don't need the problem to tell you its speed. It's always going to be traveling at speed of light. Okay, and speed of light, this number is going to be given, but I believe most people know this number. Okay, if you know Einstein, you should know that number. Okay, so in this case, this is an easy one. So all I need to do is just rearrange that equation. If I want to find frequency, I have just do V over wavelength, and the V of the speed of the E&M waves, it's always going to be this number. Always going to be this number. What is a wavelength? Okay, you should be careful. Okay, a lot of people they do this. Oh, it's 3.5 meters. I plug it in. Really carefully. The distance between a crest and a trough is 3.5 meters. Is that a wavelength? No. Right? This is a wave. This is a definition of a wavelength. But the problem only tells you the distance from between the crest and the trough. That's 3.5 meters. What is wavelength? 7 meters. Right? Okay? And then once you have that, plug it in, you can find the frequency. That's going to be B. Okay? Very straightforward. This is a special equation for wave speed. Okay? But it's still a conclusion from the definition of wave, a definition of speed. Now let's take a look at two E&M waves widely used in our life. Okay, radio waves, as I said, it's widely used everywhere, right? For communication, cell phone, radar, all these things, right? Satellites. Okay, they are usually created by a transmitter, and then they are transmitted. They're produced by the antenna, and then transmitted in all directions. Right? And then in order to receive the radio wave, you need a receiver, which is also an antenna, and the antenna is going to receive the radio wave. Okay? And that's a radio wave widely used in every day. Another E&M wave, microwave. Right? We use microwave every day. I don't think you can live without a microwave. Right? Everyone has a microwave oven at home, right? To heat food. Okay? So the range of the wavelength of microwave, take a look at the spectrum on slide 10, right? So the microwave, the name is a little misleading. People may think, oh, it's doesn't mean the wavelength is in micrometers. No, micrometers tend to -6, right? But actually, take a look at the wavelength of microwave. It's usually 1 meter to 1 millimeter. Okay. The reason that people call it microwaves is that because it's smaller compared to the radio waves, which were used before microwave technology. Okay, so it's smaller than radio wave, so that's why we call it microwaves. It doesn't mean that the wavelength is always 1 microwave. Again, they're widely used to communication, wireless. Your Wi-Fi uses microwave, and then cooking food. Okay. Now, how does a microwave oven cook food? Okay, and then that's because water molecules, they are polarized. This is a very important feature of water molecule. Okay, so take a look at the image of the water molecules on slide 14. Okay, so the distribution of the charge in a water molecule is non-uniform. So that means the center of the negative charge doesn't overlap with the center of the positive charge. Okay, so that's when we say they are polarized. They're polarized. Okay, so and then if there's an electric field, external electric field, right? Take a look at these molecules. If there's an electric field in this direction, then these positive charges, they're going to be pushed away in that direction because they feel a force in that direction. And then the negative charge is going to be pulled in this direction. Okay, so all these molecules, they're going to align with the field. So positive charges are going to be a little bit in that direction. Negative charge is going to be in this direction. So they will always be aligned with the same the direction of the electric field. If the electric field changes direction, they're going to be flipped, right? Because the positive charges, they're going to be pulled that way, and negative charge is going to be pulled this way. So if there's an oscillating electric field, okay, always up and down, then these molecules, they're just going to fluctuate. They're just going to be up and down, okay? So then these molecules, water molecules in food fluctuate, okay, and then they're gonna heat up food. So it's pretty much like they are moving really fast. When molecules move really fast in microwaves, in microscopic scale, that's temperature, right? Temperature rises, okay? Temperature is just the measure of the average kinetic energy of the molecules, okay? All right? So that's why, so this is very important. If water molecules are not polarized, you can't use microwave to cook food, okay? You can't use that, okay? So that's very important. That's very important. And then there are, if you go to the market, you can buy some microwave safe plates, glasses, plastic containers. Why don't these guys cook in a microwave oven? Because these molecules are not polarized. So they're not going to respond to microwaves, okay? The electric field is changing direction, up and down, oscillating. These molecules, they don't feel anything, okay? Because the electric field, the center of the positive charge and the center of the negative charge, they overlap, okay? So they behave, they're not polarized, okay? They don't feel any effect from the microwaves. And then if you notice that the microwaves, the microwave oven doesn't defrost very well. If I want to defrost the food in microwave, it's actually very hard. It's going to take you a lot of time, right? And you also need to turn the food over, okay, to do that. That's because in a solid, okay, these molecules, they are more constrained in a certain region because the bonds between these molecules are very, very strong. So they can only oscillate in a very small region, okay, much, much smaller than the region in a liquid. Okay, so they're still oscillating with the field, but they don't have any much freedom. So they don't really collide with each other. They don't cause a lot of heat. So that's why it doesn't defrost very well, microwave. So if you want to defrost something, it's better to use the burner or hot water instead of microwave. And if you've noticed that every time you open the microwave oven, you're never going to be worried about the steam is going to be too hot. You never need to worry about that, right? Even if the food can be really hot, okay? But you open the microwave, you never feel the steam is hot, which is very important because you don't want to get burned yourself when you open it and get the food, right? The food can be really hot, but the steam is still cool. Why? Because the steam doesn't heat well in the microwave oven. Because steam is a gas, right? The gas, the molecules in the gas, they can move very freely. Yes, they can oscillate, but they are really far away from other molecules. So again, they don't collide with other molecules. So they don't have they don't heat up. There's no, pretty much due to a lack of friction, you can think of it that way. So they don't really collide with other molecules. So that's why the temperature doesn't rise, okay? All right, so that's pretty much everything I wanted to tell you in this semester. Now I'm recording this video. I'm not sure if you're gonna watch this video or we're gonna finish this class in this room again. I hope I can see you in this room again and finish the class in this room. But anyway, either way, I want to end this class again with a quote from Stephen Hawking. So this is a very good book written by him, okay? This is the last book he wrote before he passed away. And then he didn't really finish that book. I think his daughter finished that book for him. He finished most of the book, okay? So this is the some words he wrote in that book. And then in that book, the name of the book is called Brief Answers to the Brief Big Questions. Okay, so he discussed some very big questions in the universe. For example, does the universe have an end? Does God exist? Okay, is there intelligent life in other planets? Things like that. It's a very good book. I would recommend you read it. Okay, if you have time. Okay, and then in that book he wrote, okay, I'm gonna quote that: the fact that we humans, who are ourselves mere collections of fundamental particles of nature, have been able to come to an understanding of the laws governing us and our universe is a great triumph. I want to share my excitement about these big questions and my enthusiasm about this quest. One day, I hope we will know the answers to all these questions. Okay? Be brave, be curious, be determined, overcome the odds. It can be done. Okay? Thank you. This is the end. This is the end. You made it. Okay?